Good afternoon, sir.
Good afternoon.
So, good afternoon, all of you. So, today's webinar session by Dr. Chandrashekar Shetty, sir. So, I welcome to Chandrashekar Shetty, sir, to this platform. Welcome to you, sir. So, and I also welcome to our Academy Chief Executive Officer, Dr. Ramesh, sir, and our Director, A.B. Basra, sir. And I welcome to all the attendees and teachers. So, a small introduction about Dr. Chandrashekar Shetty, sir. Sir, got it. Diploma in Computer Applications, PhD Physics from Bangalore University, and currently working on research in physics, research coordinator for DST first program, mentor DST Inspire program, Government of India. And sir, I have some teaching experience and academic responsibilities. Teaching in the Department of Chemistry Physics at St. Thomas College, Mangalore from July 2012. And is joined as a lecturer in the Department of Physics and Electronics at St. Thomas College, Bangalore from 10th July 1998. And the Research Summer Fellowship, selected for Summer Research Fellowship by Indian Science Academy of Sciences, and worked on the topic of EPR studies on magnetes at the Department of Physics, Indian Institute of Science, Bengaluru during May-July 2018. Selected for Summer Research Fellowship by South Indian Science Academy of Sciences and worked on the topic determination of the elastic constants of a nematic liquid crystal using pre-dielectric effect of Raman Research Institution, Bangalore during May-June 2013. Sir, also 20 research paper published 20 research papers which include the following journals: Material Letters, Optical Materials, Journal of Applied Physics Beta, Optic International Journal for Light and Electron Optics, Journal of Molecular Structure, Results in Physics, Journal of Optics of Laser Technology, and Material Today Proceedings, Journal of Materials Technology, Journal of Materials Research Innovations. And sir presented research papers in 14 international conferences and also extracurricular activities, worked as associate NCC officer in Army wing of NCC in the rank of Lieutenant from July 2005 to July 2009. Thank you, sir. Over to you. Sir, you are not audible, sir.
Yeah, I share the screen now.
Now audible, sir. Now audible.
Yes, yes. The screen is audible, sir?
Yes, sir.
Screen is seen.
Visible,
Okay.
visible,
Yeah,
visible.
Thank you. Let me thank the Karnataka Science and Technology Academy for this giving me this opportunity. Also, I thank all the officers of the KSTA for this unique opportunity to talk to students on my favorite subjects, semiconductors. Uh, Let me tell you what are things I am going to deal with today. First, I have to speak. I'll speak to you on history of physics of and chemistry of semiconductors, because to study any subject we need some motivation. What is that subject? Why people for generations studied their subject, and what are the important applications of that subject in normal man's application? Therefore, let me discuss few things on history of semiconductor. See, if you are aware, in the year 1782, Alexander Volta was the first person to introduce the word semiconductors. And he spoke about the materials which show semiconducting nature. That is, semiconductor, when I say today we call it as Arevahaka. Then later he could develop the pile of voltaic file, very famous voltaic file, so that he could study some
Mahadeyaga,
important.
not reachable, not reachable.
Are you able to reach me, sir?
One నిమిషం, one నిమిషం, one నిమిషం.
Yeah.
Sir, visible and audible, sir.
Thank you. Thank you. Let me continue. Yes, I
Okay.
was talking about pile of Volta, and he was the one who developed several voltages so that he can study some important properties of materials. Later, Humphrey Davy, who is known as the father of electrochemistry, in the year 1821, he developed several experiments where electrical conductivity of the materials are studied. He was interested in the influence of the temperature on conductivities of metals, particularly copper, silver, tin, lead, iron, and platinum, etc. Therefore, it also beginning of study of semiconductors. As you are aware, Michael Faraday in the year 1833, he did lot of experiments on various compounds which he prepared himself, particularly sulfides of various metals, oxides, carbonates, sulfates, and nitrates. Even he studied some important materials like mercury iodide, and he noticed very surprising behavior on these materials. That is, at room temperature, its conductivity was very low, but at a temperature of about 175 degree or so, he found metallic nature of the materials, that is, conductivity was increased. It is very interesting experiment for him. Later, John Wilman hit off. He also worked on electronic conductivity of electrolytes such as glass and other materials. His contribution to ionic conductivity of the metals also appreciable. Later, the famous Edwin Herbert Hall, E.H. Hall, who did experiments on Hall effect. Today we are very familiar with the Hall effect, where you can classify the materials in which what type of conducting elements are there, whether it is electrons or holes. Based on that, we can classify the materials. Therefore, that was the first experiment conducted by Hall where the nature of charge carriers is analyzed by him. Okay. Further, in the year 1907, Karl Baedeker was a successful person who is able to produce thin films of these metals. Even he coated sheets of metals on sheets of glass and mica. You know that today the entire industry is working on thin films, but in the year 1907 itself, Karl Baedeker was able to produce very important films using various vapor phase techniques. He produced sulfur vapors, selenium vapors, similarly arsenic vapors, and so on. Even he worked on metals like silver, copper, cadmium, lead, etc. Even copper iodide was studied by Karl Baedeker, which was very interesting phenomenon in the year 1907 or so. Later, Weiss, the famous who did lot of work on magnetic properties of the materials, he was the first person to use the term semiconductor. It was uh, written in his doctoral thesis in the year 1910. Therefore, the word semiconductor was coined by Weiss. In the year 1930, Gurdon published several papers and review articles on electrical conductivity of various semiconductor materials. And He observed that the conductivity nature of these materials change with the purity of the materials. That is, by doping additional materials, the conductivity of these metals can be changed. That is once again very important step in the field of semiconductor. Even in the year 1931, Alan Wilson again is a student of famous R.H. Fowler at Cambridge University. He published a paper on semiconductors, and he is able to distinguish intrinsic and extrinsic semiconductors. Today we are familiar. Intrinsic means of pure semiconductors. Extrinsic, when I say it is semiconductors which are doped with some other elements for useful applications. And he could even coin the words like donors and acceptors. When I say donors, the materials which can donate electrons. When we say acceptors, the materials which can accept electrons. Therefore, year 1931 is very important in the field of semiconductors. Now, today we are familiar with the transistor. That is, in the year 1947 and 48, the three famous people like William Shockley, John Bardeen, and Walter Brattain, these three people discovered transistor. Today we are familiar the word transistor. Before 1947, valve tubes are used, which used very huge amount of current for any electronic applications. Once transistor was devised, discovered by these three people, the entire industry is changed. Today, we are enjoying the facility of electronics, particularly starting from transistor, the entire industry is based on semiconducting materials. Therefore, knowing semiconductor is history so important for students to take further studies in the field of semiconductors. Let me continue. This is about my introduction about semiconductors. What is the physics and chemistry involved in the semiconductors? Now, today we are familiar with the semiconductors. Suppose somebody asks you what is semiconductor? ಅರೆವಾಹಕಗಳು ಅಂದ್ರೆ ಏನು? The group of materials having electrical conductivity intermediate between metals and insulators. This is a common answer given by students. ಅಂದರೆ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳು ಅರೆವಾಹಕ ಅಂದರೆ ಅದರ ವಾಹಕತೆಯು ಒಳ್ಳೆಯ ವಾಹಕಗಳು ಅಂದರೆ ಮೆಟಲ್ಸ್ ಮತ್ತು ವಾಹಕಗಳು ಅಲ್ಲದಿರುವಂಥ ಮೆಟೀರಿಯಲ್ಗಳು, ಅದು ರಬ್ಬರ್ ಇರ್ಬೋದು, ಮರ ಇರ್ಬೋದು, ಇವುಗಳ ಮಧ್ಯೆ ಅದರ ವಾಹಕತೆ ಇದೆ ಅಂತ ಹೇಳ್ತೇವೆ. ದಿಸ್ ವಿಲ್ ಬಿ ವೆರಿ ಕ್ರೂಡ್ ಆನ್ಸರ್ ಫಾರ್ ಎ ಸೈನ್ಸ್ ಸ್ಟೂಡೆಂಟ್ ಟು ಗಿವ್. What is the range? Because you know there are three classes of materials: semiconductors, metals, as well as insulators. But as a student of science or physics, you should remember this important table. What is this? Say, if I measure conductivity in the unit of Siemens per meter, Siemens per meter, then the value of conductivity in metals is 10 to the power 2 to 10 to the power 8. Similarly, semiconductors, the value will be 10 to the power 5 to 10 to the power minus 6. For insulators, it is too small, that is 10 to the power minus 6 to 10 to the power minus 11 Siemens per meter. Remember, students, you have to remember the value in this pattern. Either you would remember conductivity or resistivity. If you take the reciprocal of these numbers, then you get resistivity in terms of ohm meter. Here, conductivity is measured in Siemens per meter. Therefore, the conductivity of semiconducting materials in general is between 10 to the power 5 to 10 to the power of minus 6. It's a very important point to be remembered. Say here, how to vary the conductivity of these materials? You can vary in different ways. First of all, by changing the magnitude of the temperature. At what temperature you are measuring the value? Depending on that, you can change the conductivity of these materials. Similarly, optical excitation. Some materials, when exposed to light, that is visible light or ultraviolet light, they increase their conductivity. That is called optical excitation. Similarly, the impurity content, by doping these materials with certain materials which we call it as impurities to a very small extent, that is parts per million, such a small extent sufficient so that you can vary the conductivity of these materials. ಅದ ಕಾರಣ ವಾಹಕತೆಯನ್ನು ನಿಯಂತ್ರಣ ಮಾಡಲಿಕ್ಕೆ ನಮಗೆ ಮೂರು ವಿಧಾನಗಳಿವೆ. ಒಂದು, ಉಷ್ಣತೆಯನ್ನು ಹೆಚ್ಚು ಮಾಡುವುದು, ಅಥವಾ ಬೆಳಕಿಗೆ ಅದನ್ನು ಒಡ್ಡುವುದು, ಅಥವಾ ಬೇರೆ ಹೊಸ ಮೆಟೀರಿಯಲ್ಸ್ಗಳನ್ನ ಅದಕ್ಕೆ ಸೇರಿಸುವಂಥದ್ದು, ಅದಕ್ಕೆ ಡೋಪಿಂಗ್ ಅಂತ ಕರೀತೇವೆ. Look at this beautiful table. Just I am trying to explain everything based on this table. All of you know the periodic table. I have identified the column 2 elements here, column 2 elements, column 2 elements, column 3 elements, column 4 elements, and column 5 elements, finally the column 6 elements. Now, so there are a few elements named them. You can see zinc, cadmium, boron, aluminum, cadmium, gallium, indium, carbon, silicon, germanium, nitrogen, phosphorus, arsenic, antimony, sulfur, selenium, and tellurium. Okay. Similarly, in semiconductors, we have basically the elemental semiconductor. What do you mean by that? The very important criteria for a material to be semiconductor is they should have valence electrons as 4, that is outermost electrons which is incompletely filled, and there should be 4 electrons, that is called valence electrons. See, if you look at the elements like silicon, you are familiar with the atomic number. Atomic number of silicon is 14. Atomic number is 14. Therefore, you know the first cell 1s2, then you have second cell 2s2, 2p6. That means altogether you have 10 electrons. Then 3s2, 3p2, because 14, no? Say 2 plus 8 plus 4, that is altogether 14. You see that the outermost shell has got 4 electrons. You know that it can occupy 2 to the power n square, that is 392. First one 2 electrons, second one 8 electrons. Here it can have 2n square, 3 square means 18, right? 18 electrons. Therefore, you have only 4 electrons. Therefore, germanium and silicon, they will behave like elemental semiconductors in their original nature. Now, when you have more than one element, they can be called as compounds. Compound semiconductors. Look at it. I have silicon and carbon. Say carbon has, again it is in the fourth column, it has got 4 valence electrons. Silicon anyway it is in the fourth column, 4 electrons, outermost shell. If you combine them all together, 2 elements are combined to become silicon carbide. 4 electrons of silicon, 4 electrons of carbon, together 8 electrons, again shared in 2 atoms. If you distribute them equally, it will be 4 each. Therefore, silicon carbide as such can behave like a semiconductor. Same thing is applicable to silicon and germanium combination also. But they are not very popular elements because of their some other properties. We look at the next column. Here, interestingly, I combine a third column element with the fifth column element. Third column, it is say aluminum is in the third column. Okay, arsen, phosphorus in the fifth column. Therefore, aluminum phosphate. What's the advantage? Aluminum has 3 electrons in the outermost shell. Phosphorus has 5 electrons. Again, 3 plus 5, 8 electrons shared between the 2 atoms. As together, you can say it is 4 plus 4, 8 electrons for 2 atoms, or 4 electrons each for each atom. Again, they behave like semiconductors. Therefore, aluminum phosphate, aluminum arsenate, aluminum selenide, gallium nitrate, gallium phosphate, gallium arsenate, gallium selenide, indium phosphate, indium arsenate. These are very important materials for light emitting applications of semiconductors. If you look at the next column, by combining the second column and fourth column, sixth column element, zinc and sulfur, you look at it, zinc and sulfur. Zinc is second column, 2 electrons in the outermost shell. Sulfur is in the sixth column, therefore it has 6 electrons. Again, 8 electrons together shared in 2 atoms. Since 4 each electrons are present in in this system. Therefore, we call it as binary compound of 2 and 6 compounds. Zinc sulfate, zinc selenium, zinc telluride, cadmium sulfate, cadmium selenium compound, cadmium telluride. These are very popular examples of binary compounds. Therefore, as elemental compound you have silicon and germanium, and compound you can have silicon carbide, or you can combine 3 and 5th elements. Similarly, you can combine 2 and 6 column elements to get semiconductors. It's very important to understand, because any applications you have to go for more materials, which is very important. Then along with that, we can have some organic materials like anthracene, which are showing semiconducting properties. Similarly, you have thiocyanins, which are doped by various elements. Thiocyanin is one important compound in organic chemistry. Similarly, organic polymers like polypyrrole, polyaniline, polythiophene, these are the useful materials which will be always useful for us in our various applications. Next, we'll see what is the basic thing important in this type of materials. If you look at the lattice structure of these semiconductors, they possess diamond lattice unit cell. When I say diamond, it has very unique structure. You look at any point here. For example, if I look at this atom, look at this atom, it has 4 neighbors, right? So you can see 4 bonds here. 1, 2, 3, and 4. Which is an outer atom, therefore outside is extended. Look at this one, that middle one, where I have, you can see a black sized carbon atom, where it may be carbon or it can be silicon also. You see, it is bonded with 4 neighboring bonds. Again, what is very important is all this bonding is covalent bonds. Probably you heard this word, covalent bond. When I say covalent bond, bonding is taking place between 2 atoms by sharing of electrons, which is supposed to be very, very strong bond. Therefore, at every point you could see the covalent bond exists and the material possesses diamond unit cell. Diamond unit cell, lattice unit cell of the semiconductor show diamond structure. This is a three-dimensional picture of a unit cell of diamond. Now, again, I just speak about to you about the electronic configuration of silicon. You know that already I told you. See here, first shell is complete, second shell is complete, third shell has got 4 electrons in the outermost shell. Therefore, we say valence is 4. Say this is 10 means it is neon, then followed by 3s2 and 3p6. These 4 electrons play a very important role in all our applications, because of this property only materials possess semiconducting nature. Say, as I told you, they are partially filled. 4 electrons in the outermost orbit, which are partially filled, they play important role. Just we look at a two-dimensional view of a silicon crystal. Always 3 dimension is fine to imagine, whereas in 2 dimension you can identify one particular direction, say 10010 direction if I show, because these crystals have various directions, 100, 111, 101, like that. You can identify the crystal planes. Say each atom is here silicon atom. Each atom is a silicon atom. Here you can see any atom, if you look at it, say it is bonding is shown between neighboring atoms like this. Correct? Bonding is shown between the neighboring atoms. This is the bonding you can see. Each has got four nearest neighbors. Therefore, bonding force comes because of the quantum mechanical interaction between the shared electrons. You can see you that I'll speak to you a little later how the bonding takes place, how the electrons get paired between two atoms, so that bonding is complete and bonding will be very very strong bonding. That can be understood with the help of this. Let us say a crystal has n atoms. Then you know that there will be 4 n electrons and 8 n discrete levels, because each electron can be occupied in two different levels, or you can say there is a possibility that 8 electrons levels are there. Hence you can distribute these 4 electrons, 4 n electrons in 8 different discrete states. Because as you know, probably the bonding, you know how the band formation takes place. You know, any any atom you think of that, they have two energy levels. The lower energy level we call it as the valence band. Upper energy level we call it as the conduction band. Valence band and conduction band. Here, when atoms come closer to each other, the electronic levels of them are, suppose they have the almost same energy level. That is, the wave functions are able to interact with one another. Then they come closer, so that you can see them. When they come closer, you can see the continuous distribution of different energy levels. This is how the bonds are formed, or you say energy bands. And such one group of bands will be here, we say valence band. And with little higher energy, you see one more set of such bands, then they can be called as a conduction band. In between, if there is some place where bands are not found, then we call that as a energy gap or the forbidden band. This is very important in band formation. Therefore, when outermost electrons interact with each other, that is, their wave functions interact, they are going to become constructive as well as destructive wave functions. As a result, the continuous bands are formed, and these are grouped in general in two different levels. That is one valence band, other one is a conduction band. In between, you have certain gap which is called energy gap. And now you have, say, 8 n discrete energy levels. Here you could see each, although they looks very, very closer, I can identify them with the little difference in energy in each side. Therefore, we call the term discrete. It's a quantum mechanical term. Discrete means different, is distinct. Okay? So you have in crystals like silicon or germanium, energy bands of these 8 states split into two, separated by energy gap. That's what I told you. One is called valence band, other one is conduction band. If you think of the uh, very low possible energy of 0 Kelvin, then we say lower band is completely occupied, whereas the upper band is completely vacant, because electrons are at the least energy state. The other band consists of four energy states called the conduction band, which is completely empty at 0 Kelvin. Therefore, lower band is called the valence band, upper band is called the conduction band, which is completely empty at absolute zero. You can think of this, say, how the bonds are formed, how the interaction takes place, how the wave functions will interact on another. You see, S orbital is spherical in nature, whereas p orbitals always is dumbbell shape. Px, Py, Pz, three possibilities are there. It always leads to sp3 hybridization, that is, the energy distribution takes place in such a manner that one loop is going to become very small, the other one gets expanded. This type of hybridization is referred as sp3 hybridization. Here, uh, spherical symmetry is observed for S-type wave functions, and dumbbell is shaped for the shape is for P-type orbitals. And this is how you can think of, say, atomic orbitals. Say, the first one, psi 1 is the wave function representing the first atom's wave function. Second atom's wave function is represented by psi 2 when they are separated, atomic orbitals, we say. But when they interact, then what is the possibility? Say, one may become anti-bonding orbital, that is, it is going to the higher level, which is not supporting much, whereas other one is going to become bonding orbital and anti-bonding orbital. Therefore, bonding orbital is always at the lower energy level, anti-bonding orbital is always at the higher energy level. This is due to the interaction of two orbitals, quantum mechanical interaction. This is called linear combination of atomic orbitals. So this can be broadly can be shown in any picture. You can look, you can see like this. Say, insulator, you have lower energy bands are completely filled, upper energy bands are completely vacant, and energy gap is too large in between. Similarly, in semiconductors, you have filled valence band. This is valence band, empty conduction band. Energy gap is substantially small. Whereas in metals, many times we see that overlapping valence and conduction band. Similarly, even at valence band and conduction band, in both bands, electrons are present even at 0 Kelvin. This is the band structure we are representing for 0 Kelvin. This is again important point to be remembered. Therefore, energy gap in the case of insulator is around 6 electron volt. 6 electron volt, very large. Whereas in this case, we say about, say, less than between 1 to some 2 electron volt. Of course, it can vary. Even 3 electron volt we can say in the semiconductor, but in general it will be around 1 to 2 electron volt. Whereas here, if they are overlapping, you don't find any energy gap. Otherwise, energy gap may be there, but very small energy gap, which can be easily changed by changing the temperature. That is, electrons in the lower energy band can be excited to higher energy band. Again, this is a very important diagram to be remembered by the students, because any competitive examination they may ask question like this. So always we represent the energy band using EK diagram. In the y-axis I have energy, k-axis I have the momentum. This momentum means it is a 2 pi by lambda. You would remember, it is not momentum mv, 2 pi by lambda. It is a vector. K is a vector, wave vector, what we call wave vector. And energy, anyway, it is energy in the y-axis. See, what is very important here is, see, if in the first diagram you see, the K zero value of higher energy level and K zero value of the lower energy level, they are along the same line. That means to excite one electron from here, lower energy level to higher energy level, you only require energy difference, that is Eg. By just applying little energy, you can excite them to here. See, this type of energy band is observed in certain class of materials, then they are called direct band gap materials. Direct band gap materials. Whereas, if you look at the second picture, the lower energy level, E0, K0 is here. Whereas, K0 is not in the case of excited level. You can see it is not K0 here. K, some value, you can see this is the K value, energy, That means if you look at it, to excite one electron from lower energy level, you have to not only supply energy, you have to supply the wave vector also, the momentum also you have to supply. This type of energy gap is referred as indirect band energy gap. Or in other words, one electron, when it comes from higher energy level to lower energy level, it can directly undergo transition. Whereas it cannot undergo transition directly, it has to come to zero level, K0 level, and then undergo the excitation to downwards to zero. Indirect and direct band gap, where here K plays an important role. Therefore, direct band gap semiconductors, of many of them, like silicon, germanium, are all direct band gap. Whereas this band gap, the indirect band gaps, materials are useful for light emitting applications. Okay, light emitting applications. There are reasons why they show that property. Now I'll go for the little basics of intrinsic semiconductors. We say pure semiconductor crystal with no impurity or no lattice defects. There should not be any defect in the lattice. There should not be any impurity other than silicon or germanium or any semiconductor for that matter. And in such material, there are no charge carriers at 0 Kelvin. Valence bands are filled with electrons and conduction band is empty. Therefore, remember at 0 Kelvin, valence band is completely filled, conduction band is completely empty. That is at 0 Kelvin. But I always should remember, as you increase the temperature, there are some impurities, there are some defects created. Therefore, it is theoretically we define intrinsic semiconductor. Look at it. You see here, all these are silicon, this bigger circle or silicon atoms, you could see here, suppose a bond is broken, here one covalent bond is broken by some means, then you see that one electron and one hole is produced. This is a hole, one electron and hole is produced. Therefore, in pure semiconductor, always number of charge carriers, electrons, or number of charge carriers, the holes, we say P means positive, N means negative. It's always constant, they are equal in number. Therefore, we say Ni. Ni is intrinsic charge carriers. It talks about number of electrons or number of holes. But they will be equal because whenever it is broken, one pair of charge carriers are produced. They recombine, further bonding takes place. What is extrinsic now? If that is the case, it is possible to create carriers in semiconductors by purposefully introducing impurity into the crystal. This process is called doping. Remember, we have to purposefully introducing certain impurities with a purpose. Randomly, you are not putting some material. Randomly, you are not putting some other element. Without measuring, you won't do it. You do it with the appropriate measures, exact number, and with a purpose. Therefore, this process is called doping. We have N type doping, similarly, P type doping. Therefore, that will alter the equilibrium concentration of intrinsic charge carriers. By doping, we are trying to alter the intrinsic number of charge carriers. How to do it? Let us see here example. So I have example of boron. I have shown both boron as well as arsenic. What specialty of boron? Boron has outermost electrons, which are boron atomic number is 5. Therefore, 1s2, you can say 1s2, 2s2, and finally 3s1. Look at it. First shell is filled here. So this is 2p. I'll correct it. 1s2, 2s2, 2p1. First shell is filled, you have 2 electrons. Second shell has got 3 electrons. Therefore, boron, if you look at boron, sorry for that. If you look at boron, as I told you, it is boron is 1s2, 2s2, 2p1. It has got 3 electrons in the outermost shell. As therefore it is a trivalent, okay, trivalent atom. Therefore, it will have one electrons less to complete the fourth electrons. That is valence. Therefore, we call them as trivalent dopants. Trivalent dopants. When you put a boron atom in between in the place of silicon, then you see 3 electrons shared by 3 neighboring silicon, whereas the fourth electron of this has no companion. Therefore, you don't find the complete bond here. That's very important. Therefore, we say it is a trivalent dopant. As a result, it will induce one hole as good as one excess charge carrier, that is S plus, you can see H plus, that is it will as one excess of hole. Similarly, if you add arsenic, again it is a pentavalent dopant. Outermost there are in outermost shell there are 5 electrons, and you see the 4 electrons are shared by the 4 neighboring germanium atoms, and it is left with one more electron. You can see one more electron here. Therefore, we call it as a pentavalent dopant. Therefore, if you add a pentavalent dopant, it will lead to one extra electron. Therefore, one very important point to remember is by adding a pentavalent dopant, you are making N type. N refers to negative more, N type semiconductor. By adding a trivalent dopant like boron, you are making a p-type semiconductor, which will contribute one whole to the entire semiconductor. Always remember, we don't dope simultaneously both. In one side, we dope P, other one, or for other material, we dope N-type semiconductor, N-type dopants. Okay. Now, one very important device we study after knowing what is a p-type, what is n-type material, is a p-n junction diode, formation of a p-n junction diode. You would always remember, once I have a semiconductor here, it is suppose it is pure. As I told you, it has got intrinsic charge carriers, number of charge carriers n as well as p are same. But suppose I dope one end of the semiconductor with the trivalent dopants to make it p type, at the other end by a pentavalent dopants to make it n type, then what will happen is there will be a concentration difference. Say more electrons are here, okay, more holes are here. So what will happen? As a result, say there will be exchange of these particles over the junction. You see here, more and more electrons are occupied here, more and more positive charges are occupied this side of the junction. Therefore, hole try to diffuse this side because of the extra holes. Similarly, electrons try to diffuse this side. But after certain time at the junction, you see that electrons can occupy at this region near the P, and positive charges occupy A. Current one.
Hello, sir. Hello. Hello. Hello, sir. Hello. Hello. Dear students, please wait some time due to technical issues. Again is joined. Chandrashekar, sir. Hello. Shanta. ಹೌದಾ ಸರಿ ಸರ್ ಅಲ್ಲಿ ಈಗ ಅಲ್ಲಲ್ಲ ನಾನು ಟಾಪಿಕ್ ಇದು ಮೇಲ್ ಐಡಿ ನಾನು ಕೇಳ್ಬಿಡ್ತಾರೆ ಸರಿ. ಹಾ ಸರಿ 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 ಆಯ್ತು ಆಯ್ತು ಓಕೆ Dear students, please wait some more seconds due to technical issues. Again, the resource person joined. Yes, sir.
ಈಗ ಬಂತು ಸರ್ ಬಂತು.
ಬಂತು ಬಂತು ಸರ್ ಬಂತು ಸರ್.
ಎಸ್ ಎಸ್ ಎಸ್. Okay, I'll continue. Sorry for that interruption.
Please, sir.
Whether video is visible, share. Okay.
Yes, sir. Visible and audible, sir. No problem.
Our my PPT.
PPT is not visible, sir.
Okay, okay, yes, yes.
Once again, share it, sir.
Yes, yes. Sir, now whether it is visible, sir?
Yes, visible, sir. Visible,
Okay.
sir.
Oh, thank you, thank you. Yes, yes.
Okay.
I'll continue with that. I'm sorry for that. Now I'll continue with the formation of PN junction. You could see here uh, uh, P type and N type materials in the either side. As I told you, electrons will diffuse from N side to P side. Similarly, holes will diffuse from the P side to N side. But as they diffuse at an equilibrium point, there will be uh, a situation where further diffusion of these electrons will not take place. That by creating a barrier, that is what we call the barrier potential. You could see in the second picture here, the barrier potential is developed so that further diffusion of electrons or holes from either side will not take place. Hence we say a PN junction is formed. PN junction is formed. That's very important. And at this point, this barrier potential can be shown as some voltage VO. Therefore, unless the electrons or holes overcome this barrier potential, they are not able to cross the junction. This is very important in formation of PN junction. This will happen at the time of making of a PN junction. That is, one side of a slab of silicon or germanium is doped with the p-type material, other side is doped with the n-type materials, so that you see that a junction is formed. Now, what do we do with this PN junction? One important study we do is forward biasing a PN junction. That is, P side of the diode is connected to positive of the battery and N side is connected to negative of the battery, so that we say a forward bias is done. What is very important here? Once you go on applying the voltage or increase the voltage between PN junctions, it is able to overcome the barrier potential, so that electrons will start moving towards P side. Similarly, holes will try to move towards N side. Therefore, you could see the three possibilities. Without a battery is one, barrier potential, no barrier potential is applied. At low battery, that is two, when I apply the little voltage. Third one, when I apply more voltage, barrier potential is decreased. Now, similarly, I can do the reverse bias. That is, P side is connected to negative of the battery and N side is connected to the positive of the battery. That is called reverse biasing, where by increasing the higher voltage, I give the barrier potential is increased. But remember, in the first case, the barrier width is the first example. I have a function which is a voltage is shown in terms of barrier potential. You see the barrier width here. When it is forward biased, barrier width is decreased. Here, when it is reverse biased, there is an increase in the barrier width, which can be shown in these graphs. Very important graphs which you study in your PU classes. Just it talks about only the barrier potential V0, how the conduction band and valence band, the energy levels are shown here, how energy levels keep changing when you apply forward bias and reverse bias. This is how you study the voltage and current characteristics of a PN junction diode. Say the first part is the forward bias of the diode. Second, this side is negative bias or reverse bias, what we say. You see, there's a linear relationship. Okay, for the lower voltages, if you don't find the current, for example, if it is silicon, only after 0.6 volt of bias voltage, you see that linear increase in the current. In the case of reverse bias, as increase the voltage in the beginning, there will not be much current, but As you go beyond higher voltages, you see that the current flows. Therefore, you see the forward bias is measured in terms of bias current is measured in terms of milliampere. The reverse bias current is measured in terms of microampere, which is too small to measure. One more application of a junction diode is a rectification application. What is rectifier you mean? So most of the AC, the alternate current, which we produce by various means, will be alternate signal AC. But our applications, all electronic applications, we require DC, that is unidirectional current. Electrical applications like fans and light, you require AC, whereas electronic applications, we require DC. Therefore, there is a need to convert two-dimensional directional current to one-directional current. Basic application is a half-wave rectifier. You could see here a transformer, primary and secondary of a transformer. A diode is used, one single diode is used here. See, whenever positive part of the signal, you can see the input signal is this one, positive signal, this diode is forward bias. From the symbol you can make out. Current will flow only in one direction, forward bias. But, and you see, if you measure the voltage across this load, you see the voltage. Here, output voltage is visible. But when the AC is in the negative side, there is negative side of the zero, it will flow in the opposite direction this way. As a result, diode is reverse bias. Hence, there is no conduction. When there is no conduction, no current across RL, therefore, say you see that output is zero. That means whenever there is a forward bias, you find the output DC, or only for the positive off cycles of the input, you see the voltage in the output. Therefore, we call it as a unidirectional current. Therefore, to convert AC to DC, we use a diode which is half wave rectifier. This is called half wave rectifier since only first half, the positive half of the input signal is converted into DC, not the negative half. Suppose I want both halves of the signals to be used for the useful applications. Then I require two diodes. See, diodes are connected like this, diode 1 and diode 2. And you require a center tap transformer where common ground you can make out here. Here, advantage of this full wave rectifier is you can see that current will flow in the output in both directions. Here, first half, that is the positive half, you see the diode 1 is conducting and you get the output here, diode 1. For the negative half, you see that second diode is conducting and again current will flow in the same direction in the load. Therefore, you get voltage in the second part. Therefore, for whether it is for positive half or negative half, you find output in the same direction. Hence, full wave rectifier will be more efficient compared to half wave rectifier, where we make use of two diodes and output is available for both half cycles of the input signal. Hence, it is one of the very important applications of diode. Now, what are the other applications of diode? Say, diode can be used for other important applications like a Zener diode. Zener diode means it is again a PN junction diode. PN junction diode. Say this is the PN junction diode symbol. If I make the symbol like this, okay, if I change the symbol like this, like a Z, then it becomes a Zener diode. Zener diode, okay. I write a symbol like Z here, Zener diode. What is the advantage of Zener diode? It will be useful in the reverse biased condition. If I draw the characteristics of Zener diode, reverse characteristics of Zener diode, this is the reverse voltage versus reverse current I write. Then you see that there will be sharp breakdown voltage, there will be a sharp breakdown voltage suddenly, then the voltage remains constant. That is called breakdown voltage. This property of Zener diode is useful for voltage regulation applications. That is DC voltage regulation applications. Okay, this is one very important application of Zener diode. What way it differs from PN junction diode in terms of doping level? Zener is a diode where doping level is much more higher compared to our PN junction diode. Next one, photodiode. When I say photodiode, again, it is an important application of the diode for light related applications. From the name you can make out, photo refers to the light. Here, junction of this diode, when it is illuminated by light, it will conduct. That is, I have a junction, PN junction diode. I show the arrow mark that I am illuminating the junction by with the help of light, whether it is ultraviolet light or visible light. Diode will conduct, starts conducting. This is another application of a diode, which is called a photodiode. Similarly, light emitting diode. When I forward bias the diode, it emits the light. Then it is called a light emitting diode. For all lighting applications, nowadays we use a lot of light emitting diode for various applications. Even for a TV screen or everywhere you use them. Next, solar cell. Solar cell is another important application of a semiconductor where a semiconducting material is a junction is made and light is illuminated on the junction. Light is illuminated when light is illuminated, the junction will create electron and hole pairs which can be made to flow in the outer circuit so that you can generate the current from that. These are some of the very important application of the diode. In other words, semiconductor, when it is used in the form of a diode, these applications. I think I will stop here because uh, I have taken some important aspects of diodes as well as semiconductor, how it works. And these are important references. You can always refer to one important book called Solid State Electronic Devices by Ben G. Streetman and Sanjay Kumar Banerjee. Similarly, you can go for NCRT textbooks. And one more article you can find, research article, where George Bush, the European Journal of Physics, published in 1989. This also you can refer. Thank you. Any questions? I am happy to answer your queries.
ಅಂತ ಹೇಳಿ ಒಂದು ಇದು ಮಾಡಿದ್ರೆ ಸರ್ ವೇರ್ ವಿ ಯೂಸ್ ದೀಸ್ ಕಾಂಪೌಂಡ್ಸ್ ಅಂತ ಕೇಳಿದ್ರೆ
Which compound semiconductors, sir?
ಎಸ್ ಸರ್
Okay, say starting from LED, light emitting diode, or say any chip IC, what we call now IC, all are based on the semiconductor applications. What we do is, in this case, we use them in our day-to-day applications. Daily you are using in your day-to-day applications. When I say day-to-day applications means, you think of any IC, whether it's a computer, whether it is a any electronic instruments like TV, radio, or any machineries where we use electronic items. They're all made up of semiconductors. Mainly, silicon is used for these applications. Particularly, light emitting purposes, we use materials like gallium arsenide, gallium nitride, because the silicon and germanium are having the indirect band gap, which is not useful for semiconducting, direct band gap, therefore they are not useful for semiconductor light emitting applications. It requires indirect band gap, therefore we go for, I think I said other way, direct band gap is required, direct band gap that is observed in only gallium arsenide and gallium nitride. Indirect band gap materials like silicon and germanium are not useful for these applications.
Sir, Pooja Jawar asking one more question.
Yes, sir.
Sir, these semiconductor obeys Ohm's law or not?
Say this basically the semiconductors are not obeying Ohm's law. They are called non-ohmic devices because Ohm's law says voltage and current should be proportional based on the resistance. Whereas in semiconductors, Ohm's law is not obeyed for a large extent. In a small region, it may obey, but in general, what we say, semiconductors are not obeying Ohm's law.
So one more question from Shashank. Sir, does temperature affects semiconductors in any situation?
Yeah. Say there are two types of semiconductors, particularly thermistor. And I say thermistor, if I take the example of thermistor, in some cases, in thermistor applications, resistance will increase with the temperature. In some other cases, resistance will decrease with the temperature. Therefore, we call negative coefficient materials, where as temperature increases, resistance decreases. Therefore, temperature dependence is very much there in the semiconductors.
Okay, thank you, sir.
Okay, thank you, sir, so much.
So today I delivered a very good informative talk on semiconductors. So I thank you on behalf of KSTA and myself. Once again, I thank you, sir.
Okay, thank you, thank you.
So once again, I thanks to our Chief Executive Officer, Dr. Ramesh sir, and all the attendees, teachers, and lecturers. So once again, I thank to all of you. So dear students, ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ನವೀನ್ ಭಾಸ್ಕರ್ ಸರ್ ಅವರು ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಕರೆಂಟ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಸೊ ತಾವುಗಳು ಇವತ್ತು ಯಾವ ರೀತಿ ಹಾಜರಾಗಿದ್ರೋ ಇನ್ನು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ನಾಳೆನೂ ಹಾಜರಾಗಿ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನ ಹೇಳ್ಬೇಕು ಅಂತ ಹೇಳಿ ಮತ್ತೊಮ್ಮೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಒನ್ಸ್ ಅಗೇನ್ ಐ ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಸೊ ದಯವಿಟ್ಟು ಸರ್ ತಮ್ದೊಂದು ಅಕೌಂಟ್ ಡೀಟೇಲ್ಸ್ ನನಗೆ ಮೊಬೈಲ್ ಕಳಿಸ್ಕೊಡಿ ಸರ್. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್, ಬಾಯ್, ಗುಡ್ ನೈಟ್.